Everyone, as you are here today in chemistry class, I am in Raleigh looking at tractors and other agricultural equipment. But today we're still going to get through elements by their groups. I'm going to go through and talk about the different parts of the periodic table. We've talked about the different parts of the periodic table from the perspective of energy sublevels, but now we're going to talk about a bit of practical applications behind where elements lie on the periodic table, the different groups that lie on the periodic table, and so forth. So descriptive chemistry. Descriptive chemistry is the study of elements and the compounds they form. So it's looking specifically at the different types of elements that there are and what you can use them to do. Let's see. Skip that. Elements on the same at the same position on the periodic table are going to have similar electron configurations. Like we said, the valence electrons and the amount of the electrons that an element has, that is going to determine the properties of those elements, specifically the chemical properties. And so if two elements are side by side or up and down on the periodic table, they're going to have similar electron configurations, therefore similar chemical properties. The first element we're going to look at is an element unto itself. It's hydrogen. Hydrogen is essentially just one proton. It's the proton itself. Now there's different variations on that. For one, it can have electrons associated with it. Won't always, because hydrogen has such a low electronegativity that it gets its electron taken from it a lot of the time. And remember, yesterday when we were talking about electronegativity increases as we go to the right on the periodic table and as we move up it. It's the ability for an atom to hold on to its electrons. Because it has such a low electronegativity, it's not going to be able to hold on to its electrons well. Another thing that hydrogen could have is neutrons associated with it. So if it has one neutron in its nucleus, it's a deuterium ion, and if it has two, then it's a tritium. But anyway, so hydrogen is the most abundant element in the entire universe because it is what composes stars. Stars are what enable higher elements to be built, and they're built from combining hydrogen atoms together with other hydrogen atoms and adding protons to protons and so forth. It has an electron configuration similar to that of the group 1 metals, so its outermost s sublevel is filled with only one electron. And what it wants, because it is its highest electron sublevel, is the first sublevel that there is, 1s, wants to have two electrons in order to fill that up. It's a gas at room temperature, which is a property of nonmetals, even though it is in the same the same group as metals, and it can easily gain another electron or lose its one electron. It's considered a group by itself. Some physical properties of hydrogen: it is colorless, odorless, and tasteless. It occurs naturally as a diatomic molecule. Remember, it's part of the hydrogen 7 of diatomic molecules. It has the least mass of any of the gases and therefore will move faster and diffuse faster than any other gas. Hydrogen molecules have little attraction for each other, so they have low condensation point at negative 253 degrees Celsius, almost at absolute zero. It will also change into a metallic form at extreme pressure greater than 2.84 times 10 to the 11th Pascal. So it's really, really high pressure. Chemical properties. It can act like group 1 elements and lose its electron, or act like group 17 elements and gain an electron, just because it doesn't. It only has one energy-less sublevel. A mixture of hydrogen and oxygen molecules sparked by a flame will burn to form water. That's kind of interesting. You wouldn't think water being the result of a combustion reaction. It's used for fuel in spacecraft, and it combines with many elements to form very important compounds, like ammonia is 1 nitrogen and 3 hydrogens. That's the stuff that is removed from our bodies when we urinate. Hydrogen chloride and other acids are defined as having a hydrogen atom combined with another molecule or atom. And it combines with carbon to form millions of hydrocarbons. So hydrogen is essentially the filler element for organic chemistry. And we'll talk about that later. Okay, now that we're done with hydrogen, we're going to look at the group 1 metals. These are called alkali metals. So group 1 goes from lithium at the top to, I believe, francium at the bottom. These are extremely chemically reactive. So if you think about potassium, if you throw it into water, will immediately explode. That just because of how reactive it is. They have electron configurations similar to hydrogen, so they have their outermost energy sublevel at the S, and they only have 1 electron in that S sublevel. They lose this easily because they're very weak electronegatively, and they'll develop a 1+ charge to become a cation. Some physical properties of the alkali metals: they conduct heat and electricity well, they have a bright metallic luster, they have low densities, and they're very soft at room temperature. Some chemical properties: they will donate their 1 valence electron readily to attain a stable electron configuration like that of a noble gas. And if you look at the group 1 metals and you go back 1, you'll get to the period above it at group 18. So group 18 is the noble gas area of the periodic table. That's essentially what all elements long to be as noble gases, the ability to be completely chemically stable. So that's what the alkali metals are trying to achieve. Okay, moving on to group 2, the alkaline earth metals. So group 1 are the alkali metals, group 2 are the alkaline earth metals. The earth originally applied to metal oxide compounds, which are mostly geologic minerals that dissolve slightly in water. Some of these compounds are similar to compounds of alkali metals, so the names were combined. So essentially they're found in dirt. The electron configurations of these involve filling up of the S sublevel. So all of these compounds have complete S sublevels, assuming that they have as many electrons as protons. So they have 1s2, 2s2, excuse me, not 1s2, that would be helium, but 2s2, 3s2, and so forth to 7s2. Some physical properties: they are all solid at room temperature. They have typical metallic properties. They are denser, harder, and have higher melting points than all the alkali metals. Their densities are slightly higher than those of the alkali metals. Hardness is much higher, and all are malleable. So we're beginning to see that they look a little bit more like your typical metal. Some chemical properties. These are going to be like the alkali metals in that they want to lose their electrons to gain a noble gas configuration. They want to be stable like the noble gases, and they are also electronegatively weak. They're stronger than the alkali metals, but they still are weak compared to everything else on the periodic table because they're only in the second row. So they're going to give up those 2 electrons, donate them to another atom so that they can become chemically stable. So they have a relatively high reactivity, and this reactivity increases from top to bottom due to larger atoms holding their electrons less strongly. So calcium is going to be very reactive, whereas beryllium is not going to be as reactive. Then we get into the transition metals, and these are what you stereotypically think a metal of being. The first 2 groups are metals, but they're not as metallic as these. The transition metals are all the D block elements, so everything in the middle. And the name traces back to an earlier theory that the properties of these elements changed gradually into the properties of nonmetals, which is not true, but the label sticks. It contains some of the most commonly used metals, such as iron and copper. The electron configurations of these atoms all have their newest electrons nesting inside of outer valence shells. So that's where some of the chemistry gets weird. Cations can form because of this electron configuration. Some physical properties. They're reasonably hard. They have high densities. They have considerable toughness or strength. They typically have a shiny luster on freshly cut surfaces. They're ductile. They're malleable. They're conductive of heat and electricity. All of the physical properties of metals. Chemical properties. They generally have similar chemical properties, but there are also many exceptions, and these are caused by the specific quantum mechanical relationships between their electron structure and nuclear changes. Metals showing little chemical reactivity, such as gold, silver, and platinum, can resist corrosion for centuries, but other more reactive metals like iron and copper quickly corrode when exposed to moist air. Nearly 2/3 of all naturally occurring transition metals occur as native minerals, so they can be found in rocks. Now, the electrons of transition metals also act like a soup, and we'll talk about this more when we get to different compounds. But the metallic bond, or the electron C theory, suggests that electrons kind of flow in and out of these nesting electron configurations rather than remaining stuck in place relatively like in a non-metal bond or something of that nature. And then we have the intertransition metals, and these are the F block at the very bottom of the periodic table. Now, if we were to be true to form, we would put the F block in between the S and D blocks. But it's just easier to put it at the bottom instead of having a much longer periodic table. The periodic table chart would be at least twice as long if we did not do it this way. There's two rows in the intertransition metals. There's the first called the lanthanide series and the second called the actinide series. So the lanthanoid series extends from cerium through lutetium, and they are once called the rare earth elements because they were difficult to identify and even more difficult to purify from their ores. They occur in high concentrations in a considerable number of minerals and in low concentrations throughout the Earth's crust. Then the actinoid series, this extends from thorium through lawrencium. Many of these are nuclear reactive, they're radioactive. Only the first 5 elements of the actinoid series are actually found in nature. The rest have been formed only in man-made nuclear reactions. These elements consist of many radioactive isotopes that are produced artificially and are very unstable. So like we watched in the video yesterday. Physical properties. The majority of the lanthanoid series elements are weakly attracted to magnetic fields because of their unpaired electrons. All of the elements in the lanthanoid series occur naturally except promethium, and freshly cut surfaces of pure forms of these metals are bright and silvery. Chemical properties. The highest energy electrons of the intertransition metals occupy the 4f and 5f sublevels. The atoms of the elements lanthanum and actinium contain no 4f or 5f electrons themselves. Their outer electron structures resembled those of the lanthanoid and actinoid elements closely. They display great uniformity in their chemical behavior, and they are difficult to purify from samples containing other elements in the series. Okay, groups 13 through 16. These are going to get into the transition between the transition metals and the nonmetals. They consist of combinations of post-transition metals, metalloids, and nonmetals. Post-transition metals follow the transition metals on the periodic table. This is where the metals start including more electrons in the p sublevels. Some of these are well known, like aluminum, tin, and lead. Metalloids congregate around what's called the stair-step line between the cells in groups 13 through 16. So if you look at the periodic table up on the board, you can see there's, I believe, a pink strip going diagonally down to the right. Those are the metalloids. Their characteristics lie somewhere in between the middle, between metals and nonmetals. They have a somewhat metallic luster. They show a variety of colors beyond the typical silver or gray metallic color. They tend to be more crystalline and brittle with lower ductility and malleability, and they typically have fair electrical conductivity. So looking at each one of these groups, the first is called the boron group, and each one of these groups are just named because of the top element in the system. So boron has boron on top. Consists of 5 post-transition metals in a metalloid. There are significant differences between the chemical properties of boron, a metalloid, and the metals below it. Elements in this group have 3 valence electrons, which they can lose to form 3+ cations. So you remember we talked about the way to look at valence electrons is only to count the s and the p sublevels, because they're the only ones that will be on the outside. That's why boron loses 3 electrons, because it is only has 3 electron in its valence shells. So it loses those because if it doesn't have that many electrons, then the atom is essentially going to lose them. Physical properties of the boron group: boron and aluminum are the 2 most economically valuable elements. Boron can transmit portions of the infrared spectrum rather than absorb it as most materials do. It conducts electricity well, but only at high temperatures. Aluminum combines high strength with low density, especially in its alloys, and it was initially difficult to refine, but once an inexpensive means of refining it was developed, the price of aluminum decreased significantly. The ever grouped 13 metals are increasingly metal-like as their atomic numbers increase. Chemical properties. Boron has the electron configuration of the elements in group 13, but has several properties of silicon in group 14. Its small size allows the nucleus to hold electrons, as though the nucleus had a greater positive charge than it does. Aluminum corrodes in the presence of atmospheric oxygen, and that's it for the group 13 elements. Moving on into group 14, this is the carbon group. Carbon is the only true non-metal in this group. There's 2 metalloids, and those are silicon and germanium, what we use for digital electronics. The 2 metals in this group are tin and lead. And then the last element is flerovium, which is a artificial element. Carbon is more important than all the other elements in this group because of the importance it has in organic chemistry and in biochemistry. We're going to talk about those more in the course later on, so I'm going to kind of skip over them. Just remember that carbon is essentially the building block of all life. Physical properties of the carbon group. Solids. They're solids at room temperature. Flerovium is an exception because we don't really understand what it would be. We think it would be a gas. Carbon takes several forms. It could be a crystal, and as a crystal, it's a diamond or graphite. We can also make carbon nanotubes, and they have a lot of different uses. Silicon and germanium are brittle solids with metallic luster. And then tin and lead are fairly common metals that have had a lot of uses over the course of human history. Chemical properties. Carbon generally has a low chemical reactivity, although it does serve as a structure. Once it's set, it's not going to necessarily recombine into new compounds readily. One famous reaction that carbon has is combustion, which is fire. Silicon does not readily react with air, water, or acids at low temperatures. Tin is relatively inactive and is often used to plate other metals to reduce corrosion, and lead is also very inactive, especially in the presence of acids. Then we get into group 15, and these are called pnictogens, spelled with a P. So pnictogens exhibit a dramatic range of properties from top to bottom, and it starts with nitrogen, which is a gas, and it's followed by 4 naturally occurring solids: phosphorus, arsenic, antimony, and bismuth. Nitrogen and phosphorus are nonmetals, arsenic and antimony are metalloids, and bismuth and moscovium are post-transition metals. Neutral forms of these elements have 5 valence electrons, but they have an unusual ability to transfer or acquire electrons as needed when combining with other elements. Physical properties. Nitrogen normally exists as a diatomic molecule in the gaseous state. It accounts for approximately 78% of the volume of the Earth's atmosphere. And so that helps make the Earth's atmosphere inert, and chemical reactions don't readily happen in the air, which could be bad if those chemical reactions affect our breathing, right? So it's a good thing that nitrogen is so much of the atmosphere. Phosphorus does not occur as a native element because it is too reactive and exists in different polyatomic forms like phosphates, which is a compound of oxygen. All are solid forms with a variety of colors. Chemical properties. Nitrogen as an elemental gas is essentially inert, and the reason why we're getting into less reactive elements is we're in the middle of the periodic table. Not literally, but in terms of valence electrons, we are. They have, so the carbon group had four valence electrons. That's about the middle of how many valence electrons you can have. Nitrogen and the rest of the pnictogens have only 5. And so essentially near the middle. White phosphorus is extremely reactive and will burn spontaneously in atmospheric oxygen. Arsenic readily bonds with nonmetals. Antimony reacts to form compounds with hydrogen, oxygen, and halogens, forming many hydrides, hydroxides, oxides, and halides. And then finally, bismuth reacts with acids and with water at high temperatures. Group 16, the chalcogens. This includes several reactive and important elements, and we're getting to the end of how many electrons you can have in your valence state. So we're talking about oxygen, sulfur, selenium, tellurium, polonium, and livermorium. So oxygen is the most easily recognized nonmetal element in this group. It is a very common element in organic chemistry, bonds of carbon. It's involved in cellular respiration, photosynthesis, and so forth. It's good at being, I said yesterday, an electron donor. It's an electron acceptor. Sulfur and selenium are its fellow nonmetals in the chalcogens. Tellurium is a highly reactive metalloid with few industrial uses. Polonium is either a post-transition metal or a metalloid, and livermorium, first identified in 1999, is thought to be metallic. Elements here has 6 valence electrons, and they will often gain 2 additional electrons to become -2 charge anions. Physical properties. Oxygen is a colorless, odorless, tasteless gas, and it forms about 21% of the Earth's atmosphere. So between nitrogen and oxygen, you get 99% of the atmosphere. There is an ozone layer high in the stratosphere, and this is in comparison to regular diatomic oxygen. So diatomic oxygen means 2-atom oxygen. Ozone has 3 atoms in it, and ozone will protect the Earth from much of the harmful radiation from the sun. Sulfur exists in a variety of forms depending on the arrangement of its atoms. Native sulfur is a brittle, yellow crystalline solid. When heated to 115 degrees Celsius, sulfur melts into a straw-colored liquid that can crystallize into another form. Sometimes sulfur was called brimstone. So when you think of hell, when Jesus and other prophets talked about it, they would refer to sulfur being one of the things burning in hell. So selenium, it has numerous forms. It's an important mineral for your nutrition. Tellurium is a metalloid, and it comes in both a black amorphous form and a brittle silver-white crystalline form. Polonium is highly radioactive, silver-colored metal. Chemical properties. Sulfur and oxygen have similar chemical properties. Oxygen is one of the most reactive elements, having an electronegativity second only to fluorine, so it attracts electrons very, very well. Sulfur is reactive at room temperature, though it doesn't match the reactivity of oxygen. Group 17, the halogens. So we're out of those transition states between 13 and 16. So all elements of group 17 have fairly consistent chemical properties. Halogen means salt producing, and it's probably the most chemically uniform group of elements other than the noble gases. They form salts when they bond with reactive metals, specifically the alkali metals in group 1. They are so reactive that they are difficult to obtain and keep in their elemental forms. The first 5 halogens are nonmetals. The last, tennessine, discovered in 2010, is so new that we know little about it. These atoms have 7 valence electrons, which means that their electron configuration is very close to that of a noble gas. And in order to get to the noble gas configuration, they want to gain 1 electron. So they become a -1 charge anion. Physical properties. They show a definite trend in their physical properties. As their atomic numbers increase, their densities, melting points, and boiling points increase. Their colors exhibit increasingly darker hues. Fluorine is a pale yellow gas with a low density, and it's the highest electronegative element there is. Chlorine is denser greenish yellow gas. Bromine is a deep reddish brown liquid, and iodine is grayish black crystalline solid. Chemical properties. They are adept at taking electrons due to high electronegativities. They're extremely reactive, often releasing heat and light, and they are poisonous to humans above trace quantities. And then finally, the last of the elements we're going to talk about is group 18, the noble gases. These are what all the other elements want to be. They have a completely full valence shell, having 2 in the S sublevel and 6 in the P sublevel. They do not react with other elements except under unusual conditions of pressure and temperature, and that's just about it. They don't react. They're colorless, odorless, tasteless, and have extremely low boiling points, which means, of course, that they're gases. Their chemical properties tend to avoid combining with other elements, and chemists have forced all that neon and argon to combine with other elements, but these compounds were always short-lived. Okay, so now what I want you to do is go to pages 135 and 147 and read the articles on those respective pages. And I'll see you tomorrow. Bye.